Hi, I'm Alan Ross. I'm here at the IEEE PES T&D, that's a lot of acronyms, conference. This is the 2020 version that is actually being held in 2022. These interviews that we're conducting is with thought leaders on the future of the power industry. So enjoy. Our guest for this segment is Casey Ballard. I met Casey about 5 years ago at a conference and thought he was brilliant then, still think he's brilliant. He's worked with us, done articles. But Casey, thank you for joining us.
Yeah, thanks for having me.
So Casey is with DuPont, and you're going to talk a little bit about what you do at DuPont when we get to that segment. But he's also passionate about IEEE. We were just talking about that. Casey also has a great head to think of the future. So I'm going to get into the great head, and I've got a question for you.
Okay.
What are the challenges, the opportunities, the trends, pick any of them, that you see in the power industry for the next decade that we're going to have to deal with?
Okay, so I really see a difference between the challenges in distribution and power.
Okay.
So the distribution side, the challenges I see are coming from the main topics that we like to talk about of electrification of transportation, right?
Right.
Electric vehicles in the home, moving away from natural gas.
Right.
And where we see those challenges is that the load profiles change so drastically from what we're using today. Now, coupled with the need for higher energy efficiency, that really makes a challenge for the grid that we haven't seen before. Right, today when we talk about efficiency, we just add more material, right? Add more steel, add more conductor, et cetera, and you can achieve the higher efficiency. But then you're adding a whole lot more cost, which then slows down the progression of the innovation.
Yeah.
So one of the things we see for distribution is there's a way to actually shrink the active part, especially on transformers, and then you can overload with using higher temperature insulation systems. So you have this peak load when everybody arrives home and plugs in their car at the same time. The transformer handles it without loss of life. Then when everybody's at work and the load's low, your core losses are much, much lower, so you get higher efficiency and higher loading capability.
I've seen some of the graphs chart work that you all have done when you do use, I think it was a combination of an ester fluid and Nomex in an application, not just a Nomex, but Nomex is an application. And you were able to load those transformers a lot higher without degradation, and it costs more. So what you're saying is spend more money on the assets that we're doing, and you will be able to handle the load factor. Just try to bulk up what you got. You won't handle it, and you'll spend more money.
It'll be more expensive.
Yes.
So we think of looking at sustainability, right?
Right.
It's how do we get the most out of the resources we have today and not waste them. So one of the interesting ways to couple that, you're right, is higher temperature systems, right, which are solids and liquids. And there's lots of different of these systems available on the market today.
Right. But
it allows you to, again, be much more efficient because most of the CO2 generated by our electrical equipment is in the in-use phase, right? Not at manufacturing and not at end of life.
Okay.
So some of the studies show 90+% is consumed in use. So the more you can do to make it efficient for that 90%, even if it costs a little bit more upfront in materials and labor, you actually get the payback if you own the transformer and reduce losses, and we can generate less CO2 while making the grid more reliable.
So I'm going to make an announcement, okay? I am biased. I happen to think that the Nomex product is the future. So as we go down this path and you say, boy, Alan acts like he thinks that there's a real solution there, the answer is, I do. So we'll get back to that, okay?
Okay.
Now let's look at some other issues that are going on in the marketplace. Because that is a big issue, and a number of people have touched around it, but we really haven't started to get some solutions. That's a good solution. What are some of the issues that we're facing in the marketplace?
So another issue we see is as we move into smart grid, right, a term that we've talked about for a long time, pulls in smaller components, right, more of handheld size equipment that is needed for all the monitoring and sensing. And what we're finding is a lot of that comes with its own efficiency issues and power quality issues. We're trying to measure very, very small changes in signals, yet we're generating a lot of harmonics. When we bring in the different power converters and as we make motor drives more efficient. One of the interesting things there is moving to a higher frequency system, no longer power frequency of 50 or 60 hertz, but moving into kilohertz and even megahertz. The challenge we have there as an industry is there's not many materials that were designed to handle that and the temperatures that these are used at. So when I look 10 years into the future, I see a lot more medium frequency or even DC overlay versus traditional power frequencies. And that's really going to change how we protect the grid, because now the inrushes are all very different, and even the breaker settings.
You know, you are not the only person that brought up DC. The minute that we hear that, and we have an AC system, and DC, there are some acolytes, and there are some people saying there are the right applications from them, but that will have a significant impact on a grid that we're trying to standardize, when now you've got these DC systems primarily running, you know, motor systems and doing a lot in manufacturing. A lot of manufacturing companies are now looking for DC power because it is more effective for them. It does create more transients. It creates problems that they don't know about. So you got all these people rushing to create a new future, and every time we do, we create new problems, right?
That's right.
Where are those being addressed in your mind?
So unfortunately today it's trial and error, right? Maybe sometimes that's the best way to learn, but that's not really what we want to do as an industry.
Trial and error on the atomic bomb creates bombs, right?
That's right. So what we have seen is there are some universities out there that are looking at making smaller scale versions so they can do trials. One I've seen uses solar for the generation, so generating at DC, and bringing it directly into a building where they have their server rooms, right?
Wow.
Also running on DC.
Okay.
So this is one of the first systems I'm aware of that there's not an AC component driven into it.
Okay, yeah.
So therefore they remove the harmonics because they're not doing inverting and converting at all.
Right, right.
Now, is that practical on larger scales? Maybe. The other challenge they've had is in how to protect the system, because the DC relays aren't quite as sensitive, at least in the feedback I've received.
Okay.
So I do see, like for office buildings, depending on where we find ourselves, how many are in offices versus working remote, could almost operate entirely on DC, right? What's in an office? Lighting, HVAC, and a computer.
Yeah, right.
All are DC today, or very easily could be, especially with LEDs.
That's a great thought of and a great challenge. Are you allowed to say what university's working on this?
Not at this point, sorry,
Okay.
that's under non-disclosure.
Okay, and then when you're, connect me. I'd love to hear about and get a story on that, because I think solutions have to be tested and shared, and then other people who are working on it say, oh, they're doing that. I think I know somebody who's working in that area.
That's right, and medium frequency is the same. There's a university in Europe that's made an entire system, including transportation, on their campus. And they're, again, finding out how long the equipment lasts.
Yeah.
So they're pulling in what they can off the shelf, and then providing feedback to those suppliers on what failed, so then we know at least where to focus, right? You're taking it one step at a time.
We've talked to a number of suppliers here that are trying to, get to the next level. Most of them are just trying to keep up. Mm-hmm. I mean, lead times are so far in advance, they can't get the materials they want. So there isn't as much that says, hey, we could revolutionize by doing this. They're just trying to get the copper they need, get the grain-oriented steel they need to do what they need to do. Right. And I haven't heard much on the innovation side, particularly in the transformer world. Innovation of them is putting a monitor on it. That's not innovation. That's just catching up to the world there. Those are some interesting things. I'd like us to write more about that. I'd like to understand it and be involved in it, because I think it's fascinating. What I want to switch to now, I want to switch to DuPont, your work. Where is it going? Because I know the Nomex product was a product, and I know that Nomex has moved to being an application. What are you doing to help get to that next future?
So when we look to the future, it looks to be more innovation on the liquid filled transformer side, right? Okay. It's the high temperature systems we mentioned. So what we're working on is more saturable papers. So therefore the impregnation time can be less. Yeah. As the original Nomex was developed for dry type. It was developed for varnishing, right? Not for esters and mineral oils. Right. So it works, but it's not ideal. Okay. Also doing a lot more work to enable power transformers. So now we have the ability to do snouts, and N-rings, working on press rings, all out of Nomex components, so we can get to a true high temperature future where we can get the higher efficiencies as well. So that work is really focused on how do we minimize the labor impact to these products as they're going through the manufacturing site, so we don't increase the time that we need for saturability and for impregnation.
And for a transformer that can have a much higher heat signature, it does what for the client?
So it depends on the problem, right? One that we've seen in offshore wind turbines is it makes them lighter weight, and they're much more compact. So now your barge and your crane can be smaller as you're setting the nacelle up top.
Okay.
Another application we've seen is in some of our older cities where the infrastructure was maybe built pre-1940, and our load has really gone up.
Yeah.
So one example that we've actually published with is from New York City, where they needed to upgrade their substation. The options are put in exactly the same footprint or try to buy more land to expand the substation. So actually here, the most cost-effective method was with a higher temperature transformer insulation system using Nomex and ester fluid, where they could make a much higher MVA rating in the exact same size footprint and be able to switch that in and out very quickly in case of a failure.
Can these go in vaults?
They can absolutely go in vaults.
How many vault transformers do you think there are in New York City?
So the underground vault, the distribution side, thousands, but I couldn't put a number.
Yeah, that's right.
I couldn't put a number on it.
Birmingham has 450, so New York's got to have thousands. Yeah, that's a great application because you're not going to get more land.
That's exactly right. Where we also see it is in rail, right? So one of the first applications for higher temperature systems in liquid filled were the traction transformers that were on board. For the same reasons. We need to make them small and we need to make them lightweight, because then either the train's more efficient or it can carry more people or it can carry more load or cargo.
Yeah, that's excellent. Let's switch gears again. We're at IEEE. You've been involved with IEEE for a long period of time. What is the value of IEEE to you, and what do you bring as a value to IEEE?
So the reason I first got involved was for networking. Right, I was a young transformer engineer, and I wanted to understand more about the overall industry.
Okay.
Right, inside of our individual companies, it's easy to be stuck in an echo chamber.
Right.
So every idea is good because it came from within. Well, when you get to IEEE, you then get to have the healthy debate with your peers. And sometimes you're having healthy debate with your competitors.
Yeah.
And so therefore, the industry as a whole benefits as everyone shares their knowledge and really starts to build on what each other has shared.
So what would you say to a young EE coming out? In fact, we need data scientists too. The National Grid in New York hired more data scientists in 2018 coming out of college than they hired electrical engineers, which is we need a lot of really smart people. What would you say to an engineer coming out of school about IEEE?
So for IEEE and the industry in general, it's a great time to get involved. One of the things you mentioned is that we're looking for younger individuals because a lot of our senior members are retiring, right? The pandemic may have had some impact there, but we're seeing a lot of people with 40 years experience deciding to stay home for a while or go into consulting. So it's a great opportunity if you want to move up very quickly, if you're driven, and it's an industry that's not going anywhere, right? Electrification is part of our future. It's taking the place of some of the other energy sources, and it's where we see every government in the world investing today. Yeah,
that's right. So thank you for being our guest, Casey. I enjoyed it very much. I'm sure we will see each other in the digital world of content. Casey is one of our technical advisory board members at APC Media, APC Technologies. Thank you for that commitment, because that means that you help us shape our future of how we are communicating the marketplace.
All right, thank you.